So, hello everyone. This is lecture first for the thermal physics, or in this series, we will study thermodynamics and all related things. Okay, so the motive of this channel is to cover all the physics, means in all the fields, all the competitions, the NAT, GATE, JRF, TIFR, and all. And we are actually covering the syllabus. So, you can see my other playlists also. You will find there for the special theory of relativity, classical mechanics, and solid state. And nearly I completed, not completed, but there are lectures there which are in progress. Okay, so in this series we will have thermodynamics or thermal physics. Okay, so what we're gonna study? Let's first see the content we will study. That is, first we will study the kinetic theory of gases. Most of you have studied in the elementary classes, but we will see in a little detail here for a better understanding. So, kinetic theory of gases, MB velocity distribution, it is nothing but Maxwell-Boltzmann distribution in 3D, 2D, and 1D cases. The transport phenomena, mean free path survival equation, laws of thermodynamics, then thermodynamic potential, in that Maxwell relations, Clausius-Clapeyron equation, first order phase transition, then the critical parameters, that is in the real gases, TC, VC, and PC. Then we will move to the irreversible processes, the Joule expansion, also called the free expansion, Joule Kelvin, Joule Thomson expansion, porous plug expansion, adiabatic demagnetization. Then we will move to the radiations, wind displacement law, Stephen's law, Planck's distribution, that is in the black body radiations. Okay, so we'll study here them also. Then we will have some elementary statistical mechanics. We will study. This whole we will cover in 35 lectures. 35 lectures, and then we will have some advanced statistical mechanics. Then our subject will be completed. So, today we will see the kinetic theory of gases. Let's start. I request you to make notes of them, notes of this, whatever I am teaching you. Okay, it will be good for you, means for the revision purpose. So let's see what is the objective of kinetic theory of gases. It is to understand thermal properties of solid, liquid, and gases. Not just for gases, it's for solid, liquid, and gases all. To understand their thermal properties, major contribution in this were done by the Bernoulli, Clausius, Maxwell, van der Waals, Jeans. You already heard these names in your elementary classes. Now you will see how they contributed their work in physics. So they focused their attention on gaseous system and developed mathematical framework for kinetic theory of gases. Now the question is, why gases? Because gaseous system is relatively easy to understand as compared to solid and liquid. And why is so? We will see in the postulates that why it is easy in gaseous system. So what were the postulates of KTG, that is kinetic theory of gases? Postulates are nothing but the assumptions we will take that yes, this statement will follow, then we will have the results. Okay, so these should be followed, means we consider that they are going to follow. A gas consists of a large number of gas molecules, each of mass m, moving in random direction with a variety of speeds. So a gas is nothing but consists of large number of gas molecules, each having the same mass m, moving in random directions. Here we represent directions or directions with a variety of speeds. Means speed is not constant; it can be vary, or it can be in a range. Now, how many gas molecules per centimeter cube? There is this question. If there are a large number of gases, then how many molecules can be per cc or cubic centimeters? Experimental evidences say that 1 centimeter cube of space under STP, that is standard temperature and pressure, 1 atm, and you know the temperature, contains nearly 3 into 10 to the power 19 molecules per centimeter cube. So it is the experimental evidences that say that per cc there are this number of molecules in a gas. And if we see the in solid, the atomic density is 10 to the power 22 atoms per cc. That is nothing but 10 to the power 28 in meter cube, 1 meter cube. If we talk about electron density, that will be equal to the atomic density, that will be equal to 10 to the 22 28 meter cube. If we convert this into meter cube, it is centimeter cube, then it will turn out to be 25 25 10 to the 25. Then this is nothing but 1000 times, means atomic density is 1000 times in solids as compared to gases. That is, gas molecules density is 10 to the 3 times smaller than atomic density. Okay, so you get it. Just keep these numbers in mind. They will help you in the exam where the information is not given. You can use them directly. So these small numbers you should remember. It's 10 to the 28, 10 to the 19, 3 into 10, and you can make this. Okay, just remember them. The second postulate is, on the average, the molecules are far apart from each other. Means we consider that molecules are far apart from each other. That is, their separation is much higher compared to their size. Let me show you by the figure. If these are the gas molecules, okay, so this distance is very large as compared to their own dimensions of these molecules. Means if we have numbers that the distance between two molecules in a gas is approximately 30 angstrom approximately, and dimension of gas molecules is nothing but 2 to 3 angstrom. So see, this distance is very large, so we consider these molecules as point masses. Okay, so this was the second postulate. Now the third is, gas molecules behave like rigid and perfectly elastic hard spheres. Okay, gas molecules in a gaseous system will behave like rigid, perfectly elastic hard spheres. That is, collision between gas molecules, wall of vessels are perfectly elastic. You know what is the meaning of elastic? The kinetic energy and momentum is conserved when the collision takes place. And what is rigid? Which do not deform during collision. Means the molecules won't deform during collision. They will stay rigid. Now what is perfectly elastic? Kinetic and momentum is conserved. No energy loss during collision. That is elastic collision. And the example of elastic collision is the collision between glass marbles. Mechanical equivalence means we can show them in the mechanical terms. You know the glass marbles. Now there is this fourth postulate. Gas molecules are always in a state of continuous random motion. So gas molecules will never be in a rest position. They will always be in a state of continuous random motion. And what we infer from this statement, they can move in all directions with equal probability. That is, their motion is isotropic. The word isotropic is nothing but that it is same in all direction. Something which is same in all direction, that is called isotropic. Means density of molecules is uniform. So they can move in all direction with equal probability. That is, their motion is isotropic. So if you are saying that motion is on or in all directions, means no property can be defined in terms of particular direction because it's same in all directions. That is why it is isotropic. Now they obey the laws of classical mechanics. Classical mechanics is nothing but Newtonian mechanics. So all which follow the Newtonian mechanics is called classical mechanics. This also, kinetic theory of gases, follows the Newton's law of motion. No attractive repulsive forces exist among gas molecules. So we will consider that they are far apart, means that the forces of any kind of attraction or repulsion doesn't exist between the molecules or atoms. Collision duration is negligible compared with okay, this is fifth postulate, that is, collision duration is negligible compared with time interval between successive collisions. So there is this collision and then after time. So that after time is very large as compared to the time of collision. Okay, let d tau be the time of collision duration and tau be the time between successive collisions. Then d tau will be very less than tau. This is nothing but number of collisions per unit volume in a gas remain constant. Number of collisions taking place in per unit volume in a gas will be constant. This we considered. Okay, these are the postulates. Sixth is gravitational potential energy does not affect the motion of gas molecules. So we will consider the negligible effect of gravity on the gas molecules, means they will not affect their motion. Now, magnitude of gravitational force is very small, that is approximately 10 to the power minus 43 Newton, and the molecular forces that will 10 to the minus 13 Newton. That's why we don't consider gravitational force. Now, seventh postulate is all molecules do not move with same speed. There is spread of molecular speed ranging from 0 to infinity. So in a system of gases, means all molecules are moving, so they will have different speeds, means not all have the same speed. They will have a range of speed, means some can be at 0, some can be at very high speed, some can be in the average. Okay, so the evidence of this is in the finite width of spectral lines, means different speeds give different means different width of spectrum, means you have seen the black body radiation or the spectrum from any gases. When you pass the radiation, then you see the dark bands there, and they are of finite width. That's because of different speeds, means because of different speeds you get different time, and different time will give you different width of spectrum. In the spectrum, the dark bands. Okay, so that proves that all don't move at the same speed. Now, the motive of today's lecture is, first we studied the kinetic theory of gases, the postulates. Now we will follow all those postulates and find the pressure exerted by the gas in a system, in this box, on these walls. These walls. So we'll calculate what is the pressure applied by these molecules or particles on these walls. So let's see. Pressure exerted by an ideal gas. So we are considering the ideal gas, okay? Consider mu moles of gas is confined to a cubical container of side L. These we considered that mu mole of gas is inside this cubical container, whose side is L and volume is L cube. Total number of gas molecules is nothing but capital N. Number density of molecules is N by V, that is small n. Now, let's see. Molecules move randomly in all directions. To make it simple, we divide them into G groups, G subgroups. Sorry. So, they are randomly moving in all directions. Now, we divide all of them in N groups, in G groups, G subgroups. Means in each group, we have a uniform direction. And such type of groups are G subgroups we have. Such that each subgroup has and there are n number of molecules in each subgroup. Means n1, n2, n3 molecules in each 1 to 3 subgroups molecules, and move with an average velocity vi, and in each subgroup the velocity of particle is vi. So following conditions is satisfied, means total number of molecules will be sum of molecules in each subgroup, that is n1, n2, n3, ng. So all of the sum of all of them will give us total number of molecules. Now consider this group n1. We will have the particular n1 group, okay, where each molecule is moving with an average velocity v1. Okay, so there is this n1 group and all particles are moving with average velocity v1. Okay, so that v1 can be resolved in three vectors, that is v1x I cap, v1y j cap, v1z k cap, three mutually perpendicular components. Now the magnitude of v1 will be v1 square equal to v1x square, v1y square, v1z square, z square. Now it is random motion. We considered that here we have isotropy followed. Isotropy is nothing but same in all directions. So we will consider that v1x will be equal to v1y, v1y will be equal to v1z. So here we will get this result. v1 square will be 3 v1x square, or it can be equal to 3 v1y square, or it can be equal to 3 v1z square. This is speed. Okay. Now if we have this result that they all are equal, we consider them equal because of isotropy. Instead of dealing with all three directions simultaneously, we will consider the motion of n1 molecules in group 1 along any one of the three axes. Just consider the motion and along any one axis, then we will apply the result to all the axes. Okay, so let's see. Let's consider the only group 1. Take only single gas molecule. In the group 1, we have taken only single gas molecule out of N1, moving along x-axis. Now we consider this x-axis and we will see what happens. So this molecule is moving x-axis perpendicular to face A1 and A2. These faces, the molecules are moving perpendicular to A1, A2, here to here of cube. Initial momentum at face A1 is equal to mv1x. When it is here, it is moving with mv1x momentum. After traveling a distance L, that is this distance, it reaches A2 and makes an elastic collision at this phase, then go back and rebounds. So total momentum change will be, here it was mv1x, coming it was minus mv1x, so m1v1x minus this, it will give us 2mv1x. This is the change in momentum when it collided with this and came back. So the change in momentum can give us the force applied on this wall, means the rate of change of momentum. Now we have the change in momentum, we can also find the force on this face. Let's see. Distance traveled by the gas molecules before it strikes the same face. So it was going from here and coming back from here. So the distance before striking it again will be L, 2L. Let T be the time between successive collision of molecules with phase A1. Then time will be total distance upon the speed. So the speed will be v1x. So this will be the time between successive collision at one phase. Along x-axis, the momentum is imparted per second to phase A1. Now the momentum imparted on this phase A2 per second will give us force. Let's see. That is rate of change of momentum of single molecules. That will give us F1x single. Means the force applied by the single molecules will be delta P by T. That is 2mv1x divided by T. And here T we find out the 2L by v1x will give us mv1x square divided by L. Now this was the force applied by the single molecules. Now total force by the N1 gas molecules in the group 1, in the subgroup 1 will be net momentum transferred per second along x direction by N1 gas molecules. Just multiply with N1, mv1x square by L multiply by N1. That will give us total force by the first subgroup. This force is exerted by N1 molecules over a surface area on the A2. Pressure exerted by N1 gas molecules is, now pressure is nothing but force per unit area. So the force is this and area is A. So it will give us F1x divided by area is L square, and just substitute the value of F1x from here. We will get this. This is the result. So from one subgroup we are getting pressure equal to this on the wall A2. So on the wall A2 with the area A, we have the pressure by the one subgroup this. Now we have G subgroups. For other subgroups also, we will find the same result. For P2x, it will be this. For P3x, this will be this. For Px, it will be this. Now we have pressure from all the subgroups. Now total pressure will be nothing but the addition of all the pressures. The total pressure along x direction by molecules is this. Px will be Pix, P1x, P2x, P3x, P4x, all the sum from all the subgroups. That will give us this. So this will be the total pressure applied along the x direction, and it will be same along all the directions. That's why we taken this only with the one axis. Now the average speed xyz along xyz will be equal, and that will be 0 because the moment is in all directions. So net speed will be 0, but not the square term will be 0. We will find the root mean square speed. So vx square, vy square, vz square all are equal but not equal to 0. So we need to find these speeds. To put it here. Now this is the pressure, but we just get this expression, but still we need to find these speeds. So let's see. Now we have this result, vx square, vy square, vz square, and we know that these are equal, and from this equation we know that v1x square will be 1 by 3 v1 square, and v1 is nothing but this. So this will give us all the three velocities will be equal to 1 by 3 v square. V is the total average velocity. We also call it root mean square speed. So vx square will be equal to this, and this is nothing but, if we need to find the average speed, how we can find, means in all the subgroups we will have the molecules, so their total this sum and divide by the total number of molecules, that will give us the average speed v1x, v2x, v3x in all the subgroups, and there are molecules in all the subgroups n1, n2, n3, and multiply them and divide by the total number of molecules, that will give us the average speed along x direction. Okay, hope you get the idea from here. This is nothing but capital N, so this is this. Now from here we can see, this is here we have this term, we need to find this term, so we can substitute from here. This term is nothing but n into vx square, and vx is nothing but 1 by 3 v square, so we will just go with this. So px will be n vx square, in place of this n vx square m by l cube, n vx square m by l cube. So px is nothing but this, and this vx square is nothing but 1 by 3 v square, so put it here. And this v square is nothing but root mean square speed, we call it the v inside the square, not square, the inside v is called root mean square speed. So this is the pressure applied along the x direction, and this is same in all the direction, px, py, pz are equal. Or in general we can write p is equal to nothing but, this is volume v, n by v will give us small number n, that is number density of molecules, 1 by 3 m n v square, m n v square. This bar represents the average. Now equation 14, that is this, connects macroscopic parameters, that are pressure and volume, with microscopic properties such as mass and mean square velocity of gas molecules. So here what we are seeing in this equation, that we are relating the macroscopic properties, that are pressure, volume and all, with the microscopic properties or the microscopic quantities, that is the small m mass and the number of molecules, their masses. So this is how it is going. It gives pressure on one face of vessel, but it is same on all of its faces, so that's why this is along the x direction, but it is same in on all direction, means pressure will be remain same. This here, this is the vrms square, means, and this is nothing but 3 kbt by m. I will prove later how this came to this term, but this speed is equal to 3 kbt divided by m. Just remember this term always, it will came into the numerical problems that find the root mean square speed, so just use the expression and you can find. This is nothing but mean square velocity, 3 kt by m. Here kb is the Boltzmann constant and T is temperature, m is mass of one molecule. Now 14 and 15, just substitute this value in this here. What we will get? 1 by 3 mn, 3 kbt by m. mm will cancel out, 3 will cancel out, and what we will get? This is n kbt, and n is nothing but n by v, and v is multiplied here, then we will get pv equal to n kbt. This is nothing but the ideal gas equation. From here you can find the multiply with, if n is Avogadro number, then it will give you pv equal to rd. Now we already find the equations. Now there are some interpretations we can take out from these equations. The kinetic interpretation of temperature means pressure exerted by n gas molecules is, we find this expression, that is 1 by 3 mn v square, and n is here n by v. Okay, so you can write pv divided by n equal to half mv square pv divided by n. Then you can write this as 2 will cancel out, 1 by 3 mv square. So this is nothing but the kinetic energy of gases. So we can see here average kinetic energy of gas molecule, this. Now pv equal to n kbt, we just proved in the previous page. So just substitute here the n kbt, you will get kVt is equal to 2 by 3 Ke. So kinetic energy is nothing but 3 by 2 kVt. 3 by 2 kVt. So what we interpret from here, that kinetic energy of the gas molecules is only function of temperature. It depends only on the temperature, not anything else. Means whatever the pressure it is, the kinetic energy or whatever the molecule, means it doesn't matter that which molecules you are taking or which gas you are taking, the kinetic energy will be remains same for all the gases at the same temperature. This equation implies this. Now average translational kinetic energy is directly proportional to temperature only of molecules, as I already told you. Higher the temperature, faster the molecules are moving. Also from equation 3, that is this, we can interpret the root mean square speed, that is v square, can be 2 will cancel out, it will give us 3 kVt by m. So that's how we get this result. I just told you in the previous page. So this speed is nothing but vrms. So rms means root mean square, and it goes in the backward direction. First square, then take mean, then take root. First square, then take mean, then take root. That will give you the rms value of anything. Square, mean and root. Now there are some note, please write. Equation 3 connects molecular velocity, that I already told you, microscopic viewpoint and macroscopic temperature, macroscopic viewpoint, so kV. So we find that how equation 3 this relate the macroscopic property, that is temperature, with the small m mass and this rms speeds with through the kV. Second note is average kinetic energy directly proportional to temperature. At given temperature, the kinetic energy of the molecules of all gases, irrespective of the difference in masses, will be constant and same. At T equal to 0 Kelvin, the gas molecule will freeze. So according to this equation, at when T tends to 0, this whole moment turns to be 0, and the RMS speed will be approximately 0. So that's why we are calling it that molecules will freeze. So now we have some questions. Let's see. On the basis of this KTG, the kinetic theory of gases, in a period of 1 second, 5 to 10 to the 23 N2 molecules strike a wall with area of 8 cm square. Assume that molecules move with a speed of 300 meter per second and strike the wall head on in an elastic collision. What the pressure exerted on the wall? So we need to find the pressure exactly. So we know the equation 1 by 3 mnv square, or we can just do it manually, means just find a change in momentum, then the force and the pressure. So mass of N2 molecule is given this one molecule. So change in momentum is nothing but mv minus this 2 mv. The force will be change in momentum per unit time, that is 2 mv. By one molecule it will be this, and by n molecules it will be 2n mv. Now just put the value of n from here, the mass and the velocity that is given 300 meter per second, you will get the 14 newton. So this force is applied. Now pressure will be force per unit area, that will be 17.5 kilopascal. Just substitute the value, it is given 8 centimeter square, you can turn out to be 8 into 10 to the power minus 4 meter square. That will give you this result. So you can find the pressure. Now what if in this question already it also asked about the finding RMS velocity. So the formula you know for the any molecules, Vrms can be 3 kVt by m, that is m of one molecule, mass of one molecule. So it is given, then just substitute the values, and it also can be written in this form, means for the 1 mole this will turn out to be molar mass and this will come out to be gas constant 3 RT upon m. Okay, so you can use this formula also, but here you need to use this. Okay, if the sometimes that I will tell you in the next question that. So what is the note from this question? Time between two successive collisions is nothing but, if it is asked in the question that find the time between two successive collisions, and that will be 12 by v1x, and number of collisions in 1 second can be given by 1 by t, that is v1x by 12. Just remember these points if the question is asked about this. So there was this question that inside a box there are hydrogen ions, ionized ions of hydrogen, and there is this wall, charged wall, means the charge on the wall was there. So it was asked that what happened to the usual kinetic theory expressions. So the usual kinetic theory expressions for pressure, what happened to those equations if this kind of condition is there? Can we apply the all the equations or the formulas we just find? Can we? So no. The two, this was multiple selection question. So the two options were which were right. The usual kinetic theory expressions for pressure will not be valid since the ions would experience force larger than due to collisions with the walls. So this force due to electric field will be very much larger as compared to the force due to walls. That's why we can't apply those equations. And it's also the isotropy is not followed here. That's why we can't apply the laws of kinetic theory of gases. Will not be valid because isotropy is lost. Isotropy is lost here. Force is in unidirections. There is one more question. An insulated box containing a monoatomic gas of molar mass m moving with a speed v is suddenly stopped. Means something is moving and it is suddenly stopped. Then the whole kinetic energy will be turned out, will increase its internal energy and will give us temperature rise. Temperature rise. So we need to find the temperature. The increase in gas temperature as a result of stopping the box is given by. So what will be the temperature in stopping this box? So we need to see that kinetic energy will be turned out. We will use the uh, calorimetry law, that is heat lost will be equal to heat gain. Okay, so this half mv square will be equal to cv delta t. You know the cv, that is heat capacity, c equal to delta q by delta t. So you need to find the this heat, then it will be given by c delta t. So in the place of c, what we are having here, it is equal to actually 1 by n del q by delta t. So delta q will be ncv delta t, ncv delta t, and here in place of cv we written f by 2 r, f by 2 r. So f is nothing but degree of freedom, and n delta t from here. So how we write it the f by 2 r, you will understand the next, that heat capacity is nothing but du by dq by dt. Okay, and in when volume is constant, then q is turned out to be u, internal energy, and from here we can find the equation for this. Means we will use the equipartition of energy law, that is given 1 by 2 kbt in all direction energy, then 3 direction will give us 3 by 2 kbt and 3 by 2 r, then du by dt will give us 3 by 2 r. So that's how it works. So here f is degree of freedom. For the monoatomic gas in unidirection, means in a system, then it will be 3 direction will give us 3 degree of freedom. So it will be 3 here, 3 by 2, and if it is for the 1 mole, then it will be 3 by 2 r delta t, and as it is given speed v, so we will write just this, 2 will cancel out, 3 will be here, and delta t will be mv square by 3r. Just solve this equation. So it is simple. Now there is one more question. The molecules of a given mass of gas having RMS speed of this speed is given at 27 degree Celsius and 1 atm pressure. What will be the RMS speed of molecules of gas at 127 degree Celsius and 2 atm pressure? So just use the formula. We know the Vrms equal to this, and it is only dependent on temperature and the mass, and mass is same because we are using the same gas. So Vrms is directly proportional to delta t, and V1 is this, T1 is this, V2 we need to find, and T2 is this. So V1 by V2 will be this, and V2 can be found. So this will be the speed. Now there are some laws we deduct from the kinetic theory of gases we just proved. So what were those? Few elementary deductions from the KTG, that is Boyle's law. Boyle's law is nothing but that at constant temperature the pressure will be inversely proportional to the volume. So how we find it, that let's see. PV is nothing but this, and it can be written in the form of kinetic energy, that is 2 by 3 N into 1 by 2 mv square. This is nothing but kinetic energy, and we find this that it is dependent on temperature only, because V is depending on temperature only, 3 kBT by m. Okay, so this is function of temperature only. Now if T is fixed, then this whole term on the right side is fixed, so PV equal to constant, or P is inversely proportional to volume at fixed temperature. This is nothing but the Boyle's law. We can see the graph of Boyle's law. Obviously for high temperature this curve will be upper, and this will go like this: volume increasing, pressure decreasing, and upper bars represent the higher temperature. Now Gay-Lussac law, that is from equation 1, that is from here, we see that at fixed volume, if we fixed the volume and temperature is varying, then we can see that temperature on this side, right side, and volume is fixed, then P will be directly proportional to temperature. So you can see this relation from here. We see that at fixed volume, P is directly proportional to temperature at fixed V. This is nothing but Gay-Lussac law. So graphical representation will be like this. If there are three curves, then this first volume will be less than 2 and less than 3. Means higher the slope, lower the volume. How? Because PV is here. So P by T represent 1 by V. 1 by V. So higher is P by T, low is V. So that's why higher the slope, low is V. So for higher slope, V1 is less. For less slope, that V is higher. So V1 is less than V2, less than V3. Okay, hope you get it. There is one more law, means two more laws. Charles law, that is a fixed pressure. So if pressure is fixed, then from this relation we can see the V is directly proportional to temperature. That is nothing but the Charles law. So it's just same. This pressure will be less than this pressure will be less than this pressure will be less than this. So, and these higher the slope represent the lower the pressure in the VT graph. Now Avogadro law, at constant T and pressure, constant temperature and pressure, equal volume of all gases contains same number of molecules. Means there are two volumes V and V. Okay, this is gas 1, this is gas 2, and temperature and pressure is fixed. Then this volume will have the same number of molecules of this gas as this gas. Equal volumes of all gases contain same number of molecules. Consider two gases at same temperature and pressure. Then this will be equal. 1 by 3 m1 n1 v square equal to 1 by 3 m2 n2 v square. This will be equal. Now we will prove that molecules are equal from here. So from here we can see that half m1 v1 square will be equal to half m2 v2 square, because T is constant. T is constant, then this speed will be remain same and it will cancel out, because this speed depends only temperature. So this will be equal to this. Now half will be cancelled out. Now from these two equations we can means okay, let me repeat this again. Pressure will be equal, okay, and this is a different equation, means the kinetic energy will be equal of both the gases, because temperature is constant in both the gases, temperature is constant. Now from these two equations we can see that m1 v1 square here, m2 v2 square here, and this will cancel out. Remaining will be n1 and n2, so they will be equal. So at constant temperature and pressure, equal volumes will contain the equal amount of molecules, n1 n2, that is n1v equal to n1 into by v, we will cancel out, n1 equal to n2. So hence proved. So we will end today's lecture here. We'll move forward in the next lecture. So just share this lecture to more and more people, and let them know that there is something happening, means I'm providing something. Okay, so thank you for watching.